Hello, welcome to the IB2d video tutorials. This is tutorial 1, which will cover an introduction to the immersed boundary method. In particular, we'll try to motivate why we want to study fluid structure interaction problems in general, what the immersed boundary method is, what freely available software currently exists, and what the purpose of IB2d actually is. So to begin, we'll give a gentle introduction to fluid structure interaction problems that people have thought about before, and then we'll turn to a quick description of the immersed boundary method in a nutshell. And finally, we'll introduce IB2d, our free software that's available online that can be applied to many different fluid structure interaction problems in 2 dimensions. Okay, so let's begin. So to motivate why people want to study fluid structure interaction problems, you could think about applying this to lots of different scenarios, such as how different organisms move around in fluid environments, such as jellyfish. Or you could think about these problems being applied to some more human physiological processes or physiological processes in general, such as cardiac fluid dynamics. And of course, people care about these types of problems all over the place in engineering, such as the design of airplanes, the design of automobiles, as well as how to configure different windmill farms. So whenever we have an object that's immersed within a fluid environment, whether it's a jellyfish, a heart, an engineered structure, really what we think about is the object and the fluid interacting with each other. And this is essentially the spirit of fluid structure interaction. In particular, so far scientists have spent a lot of time trying to model this type of phenomena. For example, Alexander Hoover has used 3D immersed boundary simulations to study jellyfish swimming performance. I have used the immersed boundary method to study cardiac fluid dynamics in different stages of heart development, as well as begun to look at sort of different configurations of vertical axes wind turbines. All of these types of problems have a fluid and a structure interacting with one another. All of the simulations I have just showed you have been done using the immersed boundary method. So let's discuss what that actually is now. So the immersed boundary method was first developed by Charlie Peskin in the 1970s to study blood flow past heart valves. What it actually does is it solves the coupled equations of motion for an elastic incompressible structure that's within some type of viscous incompressible fluid environment. So in particular, it solves the incompressible Navier-Stokes equations, which are the first 2 equations listed on this page, which basically just describe the conservation of momentum and conservation of mass of a fluid. The remaining 2 integral differential equations basically describe how the fluid as well as the structure can communicate with one another. And they do so using delta function kernels. Basically, the idea is when the structure moves and deforms, there's going to be a deformation force pushing the structure back towards its preferred position. And we want the fluid that's nearest the structure to basically feel the effects of that force. Likewise, when the fluid is moving, we want the structure to move at that same fluid velocity local to all the structure points. So the way we can think about the immersed boundary method are 2 separate grids. First, we have this one grid that's rectangular, known as the Eulerian frame or the Eulerian grid, and this is the fluid grid. These aren't individual fluid particles that are moving all over the place like billiard balls, but instead these are positions that essentially we're throwing down a velocity probe and measuring the fluid velocity at these positions throughout the simulation. Now on the other hand, we have the actual immersed boundary, or what we call the Lagrangian frame. And this is a structure that's allowed to deform and has some type of physical material properties that govern this types of deformation. But in practice, this is what we think of as the actual jellyfish, our heart, an insect wing, a cell, or any type of structure we have within the fluid. And now we can think of both of these grids essentially lying on top of each other if we want, although all the communication is really done through those integral equations I showed you a moment ago. The one thing we have not talked about yet, though, is we've sort of mentioned that this Lagrangian structure has some type of material properties. But we really haven't said where these material properties come from. Well, since this is a discretized mesh, we can think about these individual Lagrangian points. And we can think about adding some type of connections between these Lagrangian points using some type of constitutive laws, even things like beams and springs. So you can think of almost these beam or these springs that we had in sort of introductory physics, but we can connect all these points around our structure if we want the structure to do something like stretch or compress, whereas we can think of a beam as a material property that allows things to flex, kind of in the transversal plane. Now, what's going to be special about IB2d is we have the ability to implement a lot of these different types of material properties models that we call fiber models. We'll discuss the details of many of these fiber models later, but for right now it suffices to say that these fiber models are one of the aspects that make the immersed boundary method truly powerful. We can add a lot of different types of constitutive laws to describe how we want this material that's within the fluid to essentially flex and deform. Now we'll describe what a typical time step in the immersed boundary method looks like. You can imagine that if we have 3 points that really want to be in a line or a linear formation, what can happen is if one of these points is stretched away from that ideal formation, there's going to be some deformation force that's pushing that middle point back to its preferred position. These deformation forces can be computed, and then we can spread them out to the nearest fluid points. You can note that this is done through those integral equations, or the integral equation relating force, and you can see that the fluid points or the Eulerian points nearest the Lagrangian point where that deformation force is coming from feel the biggest effects, and the force tapers off from there. Next, after we've computed this forcing term onto the fluid grid, we can go ahead and update the Navier-Stokes equations. Another nice aspect of immersed boundary is we're not constrained to one Navier-Stokes solver in particular, but you can use a multitude of different methods if you wish. After you complete the update of the fluid velocity, next you want to update essentially how all of these immersed structure positions are going with respect to the local fluid velocities. That is to say, basically, we want to satisfy the no-slip condition on this immersed structure. And then once these immersed structure points have moved, possibly there could be new deformation forces arising from the configuration not being in its preferred position. So this is essentially one time step of immersed boundary in a nutshell. More or less, forces are computed onto the fluid by the boundary. This spreading of force is then put onto the fluid equations in which we update how the fluid moves. When the fluid moves in a new way, it's going to affect the way that the boundary moves, and once that boundary moves, there's going to be new deformation forces that are arising, and then new deformation forces that can be spread onto the fluid grid. So essentially, the immersed boundary does exactly what you think it would do at every time step. If that structure is not in its preferred position, or that structure wants to move somewhere, there's going to be a deformation force coming from its material properties that pushes or that exerts a force onto the fluid. Once that force pushes the fluid's going to move in a new way. Once the fluid is moving in a new way, it can go ahead and affect the structure in return, causing it to deform differently or move, so we have this very cyclical behavior every time step. Next, let's actually start introducing some of the free software that's available online. We'll focus a lot on our software called IB2d, which is Immersed Boundary Method in 2 dimensions. But there are a plethora of other codes that are available online. In particular, I'd like to also mention Boyce-Griffith's IBAMR package. So if we're comparing IB2d versus IBAMR, IBAMR is a powerhouse code. It can run very highly resolved simulations. It can do 3D applications. It has very extensive built-in frameworks, and it's very fast using adaptive mesh refinement as well as parallelization. IB2d, on the other hand, was developed to run codes very locally on your own machine as a way to prep simulations for IBAMR or get used to kind of this immersed boundary framework in general. It can be used for getting preliminary data as well as higher resolved data for research. It's a good tool for teaching fluid structure interaction or just immersed boundary in general. And what's really unique about it is you can implement and test new fiber models rather fast, as well as implement and test new fluid solvers as well. So again, IBAMR is Boyce-Griffith's code. It stands for Immersed Boundary Method with Adaptive Mesh Refinement. It's adaptive, parallelized, can be used for 2D and 3D simulations, and is also freely available online. Now what makes IBAMR very fast is its adaptive mesh refinement, or AMR. If you're unfamiliar with AMR, you can think of it as a way of really finding highly accurate solutions near regions where there's a lot happening. Moreover, basically in regions very near your boundary, you're going to have very highly resolved solutions. Whereas away from your boundary, where there's not as much activity, you're going to use a very much more coarse grid. And the idea is the more highly resolved regions take longer to solve, whereas these coarse regions are very fast. In IB2d, we do not have AMR, so we only resolve the full entire mesh at one particular resolution. So for example, on the left we have an IBAMR example illustrating that the closer you are to this elliptical object, the more highly resolved your mesh is going to be. Now to capture that same type of resolution around our object, in IB2d, we need the entire grid to have that resolution. This can of course slow things down dramatically. However, adaptive mesh refinement is very non-trivial to actually implement. And for the goals of IB2d, we do not wish to try and compete with IBAMR in this capacity. But that opens the question, why actually use IB2d in general? Well, for one thing, I said it can be used as an educational tool, either getting your hands wet or your feet wet and doing fluid dynamics in general, or actually getting used to immersed boundary frameworks. So in particular, if you just want to get your feet wet in immersed boundary, just using IB2d, all it requires is either MATLAB or Python. There's 2 fully functioning versions, one in MATLAB and one in Python, for whichever high-level programming you prefer. IBAMR, on the other hand, because of its sophistication, it depends on a lot of external libraries. All these libraries are, of course, free online, but it is a lot to install. The other thing, when we actually try to visualize our data, both IB2d and IBAMR both can visualize using open source software such as Visit. In IB2d, we export our data using VTK files, which means you can read them using Visit or ParaView as well. When you actually go back and try to do data analysis on your simulation results, there's a built-in data analysis package that comes with IB2d. IBAMR, you can do those same things by writing scripts in either Python or MATLAB, but it's a little more tricky because of the adaptive mesh refinement. You'll have to write your own scripts to interpolate the data between all these different grids with different resolutions. It's slightly non-trivial, but can be done. Now, as I alluded to before, one of the things that makes the immersed boundary method rather elegant and rather powerful is this ability to create all these different fiber models, which describe the deformations of our structure undergoing different types of forces coming from the fluid. In particular, the immersed boundary literature has a lot of these different types of models. Things like springs and beams, which we mentioned before, but also other things called target points, porosity models, mass models, different types of contact models, and coagulation aggregation models, as well as various kinds of muscle models. What makes IB2d rather unique is that in IB2d, we've been able to actually implement all of these different types of fiber models. In addition to the fiber models talked about on the previous page, IB2d also offers a lot of other functionality on top of those, such as advection diffusion solvers, various kinds of electrophysiology models. However, IB2d doesn't have adaptive mesh refinement, it's only in the beginning stages of becoming parallelized, and it also doesn't offer a hybrid finite difference and finite element formulation of the immersed boundary method. On the other hand, IBAMR offers all of this additional functionality. What we'll do now is try to make you more familiar and acquainted with a lot of these different fiber models that are offered in IB2d. As we talked about before, there's things such as springs that could come in the flavors of linear, nonlinear, or damped that describe how two Lagrangian points can compress or be stretched apart. There are also torsional springs, in which we call beams, which also help basically make motion in the transversal plane. We briefly described some of these earlier, but there's also non-invariant beams as well available in IB2d. There are also what's called target points, which can be used for the purposes of trying to keep your immersed structure nearly rigid, or where you can prescribe motion of your structure itself. There are massive points which should come with or without the effects of gravity. You can think of these massive points such as, like in cartoons where you have a character that has a ball and chain wrapped around its leg. The more force that character pulls, the further he's going to be able to pull that ball and chain. This is exactly how these massive points work. You have your regular Lagrangian point that's tethered to one of these, quote, kind of ball and chain or massive points. There are also porous points based on Darcy's law, where you introduce basically a slip velocity such that fluid can move through your structure. There's also poroelasticity based on Brinkman equations and Brinkman analogs that more or less says the more your object flexes, the more fluid that's going to be allowed to go flow between it. There are also various kinds of muscle models, such as force-velocity length-tension relations available, as well as three-element Hill models as well. There's also artificial forcing. It's the method in which we can use to basically make the fluid move in a particular way. So for example, rather than defining an inflow condition, we can just define a fluid to have a specific type of velocity profile we want by introducing a penalty force into the fluid grid. Next, we'll introduce you to some of these examples so you can see how these fiber models are used and implemented in IB2d. The first example I'll show you is this example of rubber bands where you have a porous rubber band and a non-porous rubber band. And this is one of those fluid structure interaction very quintessential problems. You have a stretched out rubber band, you release it, and it's going to oscillate to its lowest energy state of a circle. So the porous rubber band is on the left-hand side, the non-porous is on the right. And this example uses both springs as well as porous points. And you can see that the porous rubber band is losing volume over time. The next example I'll show you is one of a flexible beam. This beam is being tethered down on the ends by target points, and it's comprised of both springs as well as torsional springs. The torsional springs are what want to give this beam its curvature. The preferred curvature in this case is a straight line. As you can see, this beam is starting off flexed, so it's going to wobble and oscillate until it becomes more straight. The background color map that you see in this video is the magnitude of velocity, and you also see the velocity field. This next example I'll show you involves using target points. Rather than trying to hold a Lagrangian structure fixed, we're trying to prescribe the motion of your structure using these target points. And what this example is going to do is we're going to prescribe the motion of all these target points to spell out different words. In particular, in this example, you can see that the words we're spelling out are basically asking someone you like out on a date. The background color map you see is of vorticity, and you can see the vector field or the velocity field as well. This example I'll show you uses a multitude of different fiber models. In particular, what you're going to see are these 3 different balls, where these balls are going to drop under gravity. However, there's going to be an upwards flow that's equal in each channel to try and resist that falling due to gravity. Now, the mass of the ball on the left is the least heavy, whereas the ball on the right is the most heavy. So this example uses target points to hold the channel walls fixed. It uses massive points to give the masses to each ball, and it uses both springs and beams to maintain that ball's curvature. Also, we use that artificial forcing to induce a velocity profile that's equal in each channel going upwards. Let's see what happens. Now, as you can see, on the far left, that's the lightest ball. It's getting pushed upwards, whereas on the right side, we see that's the heaviest ball, and basically gravity is winning in that case. And in the middle, we have that gravity is essentially being balanced out by the upwards flow. Next, we present this example of seagrass undergoing oscillatory flow. This example is comprised of target points, which create basically the bottom and the top of this channel in which the seagrass is placed. The seagrass itself is comprised of both springs and beams, as well as poroelastic elements. Remember that these poroelastic elements, essentially when this structure flexes, this is going to be what's allowing flow to move through it. As well as we also have this artificial forcing to create a velocity profile to go back and forth in the channel. Let's see what happens. We can see that flow begins moving left to right, then reverses direction going right to left, and continues that process going back and forth. As the seagrass moves and deforms, it's shedding vorticity off of it. The next example we'll show you is an undulating swimmer. This swimmer is comprised of both springs and beams, and in particular, all it's going to do is interpolate between 2 different preferred beam curvatures. Let's see how this thing swims. You can see it begins to successfully move left to right. The background color map here illustrates vorticity, so you can see as it's changing its curvature, it's shedding vortices basically off of its tail. Now, we've said previously that there's a data analysis package in IB2d, in which you can use to analyze any of the Eulerian data, meaning the velocities, the vorticity, the pressure fields, or even track positions of the Lagrangian points themselves. In this example with the undulating swimmer, we just ran 2 different cases. The case in red is the one in which you just saw, and all we're doing is comparing 2 different undulating swimmers who are changing their curvatures with different frequency. And we're just tracking the rightmost point on each swimmer to basically see how far it's swimming versus how many strokes it has performed. The next example I'll show you actually doesn't involve any Lagrangian points or immersed boundaries in the middle of our domain. We essentially have aligned our domain on each side with target points. And these target points are more or less a way just so fluid doesn't go through the boundaries in a periodic fashion like usual. And what we're trying to model here is a Rayleigh-Taylor instability. So we also have a background concentration gradient and Boussinesq approximation as well. So we have a heavier fluid sitting on top of a lighter fluid in this example. Let's see what happens. And you can see as the instability starts, part of the heavier fluid quickly falls to the bottom of the tank, and then you see the very beautiful progression of a traditional Rayleigh-Taylor instability. In this next example, we have again the Boussinesq approximation and a background concentration gradient. However, this time we have a lighter fluid sitting on top of a heavier fluid. We still have that the outline of each domain is aligned by target points. However, this time we also have massive points constructing basically this circular object or this sphere. And we also have this sphere composed of both springs and beams to help keep its curvature and shape. As these spheres fall downwards under gravity, they're going to basically entrain some of the lighter fluid as they fall into the heavier fluid section. Let's check it out and see what happens. In the case on the left, we have a higher viscosity fluid, and let's see what happens when this sphere tries to fall through it. Now as the sphere falls downwards, it's clear it's bringing some of that lighter fluid down with it. And as you can see, the tail is rather thin and getting really stretched. Now let's see what happens to the case on the right where we have a much lower viscosity fluid. You can again see as the sphere falls downwards that it's bringing some of the lighter fluid downwards with it. However, this time that tail is much thicker. Now the last example we'll show you is one of a linear heart tube. This heart tube uses a plethora of different types of fiber models and functionality. So the heart tube itself is comprised of springs and beams. There are also some massive points in it, as well as target points to hold down the ends of this heart tube. Now, across the heart tube itself, we have different types of muscle models as well appearing. In addition to those fiber models, we're also incorporating some extra functionalities such as advection diffusion, like the previous few examples. However, this time we're also incorporating a calcium dynamics model that feeds into an electrophysiology model given by the Fitsu-Nagumo equations, in which models the propagation of action potentials which will actually initiate the heart tube pumping. Now let's actually see what happens. Again, this is a fully coupled fluid structure interaction problem that's being done by IB2d. It's using an electrophysiology model to govern the propagation of action potentials which when they travel along the tube are actually initiating the heart tube contraction. And it's clear that there's a lot of moving parts in this one example alone. But this shows you that IB2d can be used for some complex and sophisticated models in 2 dimensions. IB2d is freely available at github.com. There are 2 fully functioning versions of the code, one in MATLAB and one in Python. Also, the software comes with over 60 built-in examples that you can just download and run right away. And as of January 2018, there are 3 published papers out on this software. Our first paper was in 2015 in Integrative and Comparative Biology, then in 2017 in Bioinspiration and Biomimetics, and at the very end of 2017 in Mathematical Methods and Applied Sciences. So please go check those out. And there are far too many people to thank for general conversations about the immersed boundary method, as well as suggestions and ideas for what to incorporate into the code. I'd like to also thank all the co-authors, as well as people who have helped me develop this software, namely Laura Miller, Austin Baird, Christopher Strickland, and Aaron Barrett. I would also like to thank Boyce Griffith for the original inspiration for this code as a learning tool for IBAMR, as well as Charlie Peskin for the original development of the Immersed boundary method. For questions, comments, ideas, or suggestions for future model incorporation, please email me. I'm Nick Battista, or check me out on Twitter or my own personal webpage. Thank you for checking out IB2d, and happy computing.